Okay, so in this video, we are going to see what happened for the sample mean and the sample variance, and in fact, the corrected sample variance. And in particular, okay, what happened in the case of Gaussian distribution, and to see how it is possible to build in this situation exact confidence interval, okay, for a finite set of observations. Typically, okay, in the previous session, we have seen how to build for the sample mean and the sample variance, or the corrected sample variance, confidence interval from the mean square error. That is, we use the Chebyshev inequality, and in this way, we are able to build approximated confidence interval for a certain level. And now we are going to see what happened for the case of Gaussian observations. Okay? So I will, excuse me. Okay, so we are in the situation. So here, keep in mind that we are going to do strong hypothesis, that is x1, xn, my observation would be IID n, let's say mu with my preceding notations, sigma square, okay? And don't forget this, because what we are going to say won't be okay for other type of distributions, okay? So you are going to see that the result we are going to prove, okay, will be linked with distribution that we have already seen together, and that are the chi-square distribution, the student distribution, and the F distribution. And particularly for the student and the F distribution, it was the aim of your homework. And I remind you that the correction of my homework is on my website, okay? So let's start, okay, with a very basic thing concerning Gaussian distribution. So let's do the job this way. So here, for the moment, okay, we consider a sample of the N01, okay? So I have data IID N01. I remind you that if you have X that follows the N mu1 sigma 1 square, if you have Y that follows the N mu2 sigma 2 square, and if they are independent, we have proved together using, for example, the moment generating function, that the sum, okay, follows the N mu1 plus mu2 sigma 1 square plus sigma 2 square, okay? I have this one. So what we are going to do here, we are going to be interested in the sample mean. So in this situation, okay, xn over line, that is equal to 1 over n, the sum from I equal to 1 to n of the xi, okay? Each of them being n01, okay? So here I have n01, and I do the sum of n independent n01 using this result, okay, successively. I have the fact that this quantity follow the n0 small n, and so that this quantity follows the n0 n over n square, in fact. So that's why I have this result. The fact that xn underline follow a n0 1 over n. I remind you the following result. If you have 8 times n0 1, this is equal in distribution to n0 a square. It's what I use here when I multiply by 1 over n. Okay, so I have this first result here. Okay, I have this first result. So we are going to prove partly the second one here, and after we are going to see, okay, how to generalize this result to the case where, okay, I don't have n01, but I have n mu sigma square, okay, and typically for this one. But first I want to prove now the second one here, okay? So we are going to do the job in the next part. So this one. So let's do the proof of this one, okay? So the proof of this one is not that simple, okay? Because it's not that natural, this result, because you have here xn over line inside here, and you have also xn over line inside here. Okay, so a priori, you have here xn over line, and here something that depends on xn over line, but in fact, you have independence, okay? You have independence. So we are going to do the job together, okay, of this proposition for, I will do the proof for n equal to 2. Because for n that is strictly greater than 2, okay, in fact, in order to do the proof, I will need to use, okay, some results concerning linear algebra, okay, and in fact, diagonalization of variance covariance matrix, okay, and I don't want to spend time on this course because it's not that fundamental for what we are going to do, but just to show you, okay, what are the underlying property that allow to obtain this result. And in the case for n equal to 2, okay, you will see that you have already, okay, interesting argument in order to do the job. So when n is equal to 2, I have xn over line, that is just the mean between x1 and x2. Okay, I have this one. If I try to compute the sum from I equal to 1 to 2 of xi minus xn over line square, so I obtain two terms in my sum. I will obtain, in fact, I will obtain what? I will obtain x1 minus x2, okay, over 2 square. It's the first term for I equal to 1, and because xn over line is equal to this quantity here, plus, in fact, the same here. x2 minus x1 over 2 square. And I said that this way, you see that here you have a function f of x1 minus x2 here. And so I will have my result that is in this situation xn over line independent of the sum. Okay, if I can prove that x1 plus x2 is independent of x1 minus x2. And I will give a name, I will call it y1, and I will call it y2. And in fact, if I remind, you have here, okay, to prove that if you start from 2 independent and 0, 1, okay, x1 plus x2 and x1 minus x2 are independent random variable, okay? So And typically here we are in the setting where we are going to use result concerning Gaussian vectors, because x1 and x2 being independent Gaussian random variable, I can see easily, and it's something I have done, okay, if I remind in the list 8 of exercises, okay, you have y1, y2, that is a Gaussian vector. And so in this situation, y1 independent of y2 is equivalent, because I am in the setting of Gaussian vector, to the fact that the covariance between y1 and y2 is equal to 0. Okay, so I have to compute this covariance to deduce simply the independence in this case. And here, basically, okay, if I compute this covariance, I obtain the following. I obtain the variance of x1, in fact, simply minus the variance of x2, because the terms with the covariance between x1 and x2, okay, simplify. And of course, x1 being n01 and x2 being n01, each variance here is equal to 1. And so I obtain 0. So you see that even in the case where n equal to 2, even in the case where n equal to 2, this result is a consequence of the fact that here I have independent Gaussian random variables that are in fact simply a Gaussian vector. Okay, that are simply a Gaussian vector. Okay, so I have proved this theorem. So this one in grid generality because it's easy, and this one at the very least for n equal to 2. So let's continue to see in particular, okay, how to apply the first result. So I said that in this situation here, okay, I want to obtain for the first point, and even for the second, but you will see the idea. For this one, okay, I want to be able to say something about n observations, okay, n sample of n mu sigma square. The idea is to pass from a statement from that have, okay, inside the n01 to something that have n mu sigma square. And as you know, okay, it is possible to transform n mu sigma square into n01 this way. xi minus mu to be centered divided by sigma in order to be with variance 1. So yy follows the n01, okay, and the y1, yn are independent because they are function of xi and that the xi are independent. Okay, so it means that I can apply this result, this one, okay, to the y. So I know that y I, or excuse me, I can write this, okay, tick. Excuse me. Yn over I is equal to what? Okay. Yn over I follows the n0 1 over n. And what is this quantity here? Okay. This is simply 1 over sigma, okay, the sum from I equal 1 to n of xi minus, not y here, but mu. Okay, so I apply my result and I have to forget here, I have forgotten here the 1 over n. Okay, so I deduce from what I have proved in the case of N01, okay, by this transform, okay, two things that may apply to N mu sigma square. So if I have here, okay, x1, xn, okay, that are I, d, n mu sigma square, then, okay, I can say that xn over line, excuse me, I can say that 1 over n sigma sum I equal to 1 n xi minus mu follow the n 0 1 over n. Okay, so it's the logos of the statement for n mu sigma square instead of n 0 1. Okay, so if I do the same for this one, okay, so I know what is xn over line in my situation here. So I can apply this result to say that 1 over n sigma sum I equal to 1 to n of xi minus mu. So this one, okay, will be independent of what? Okay, of a term here that I will write, with me, I have n here, and I want to express this term here. So it's the sum from I equal to 1 to n of what? Of xi minus mu over sigma, okay? And then I have here minus 1 over n sigma sum I equal to 1 to n of xi minus mu, okay? And what is this situation here? Simply, so I have some simplification. I have simplification between the mu here and the mu here, in fact, because I have the sum of the mu here. So it is minus minus, that is plus n times mu, but divided by n. So at the end, I obtain the sum from I equal 1 to n of xi minus xn over line, okay, square, because there is a square here, over what? So if I remove the sigma inside, okay, I have over sigma square. So this one is independent of this one. And in fact, it implies that this term, okay, that is just up to constant xn over line is independent of this one. And so it implies that this one is okay if the x1 xn follows n mu sigma square according to my little computation, because I repeat that here, what do you have? You have just, okay, you have just xn over line, okay, divided by sigma minus, okay, minus what? Minus mu over sigma. So this one, that is an affine transform of xn over line, is independent of this one, that is a linear transform of the sum of the xi minus xn over line square. And so I deduce from the independence of this quantity and this one, the independence of these two quantities. So this one works even in the case when I don't have standard Gaussian random variables, but I have general random variables. And for this one, I have to adapt a little my result. Okay? So I have this one. And I want in the next part, okay, just after, to show how I can use this result here. Okay? I can use this result in order to build confidence interval for the mean of Gaussian distribution. So I add here, so I am here. I will add a new page. Okay. So I want to build confidence interval for mu from x1, xn that are IID and mu sigma square. And the idea is to use what I have done just before, that is to use this result here, okay, to use this result. So I know that 1 over n sigma sum I equal to 1 to n, okay, of xi minus mu. It follows the n 0, 1 over n, implying in particular that if I multiply this quantity by the square root of n, I obtain n01. Okay? So I have the fact that 1 over the square root of n sigma sum equal to 1 n xi minus mu follow the n01. And in fact, you will see that in statistics, so I have here something that is an estimator, okay, because it's just a function of x1, x10, a regular function of x1, xn. This estimator is called a pivotal quantity. And what is a pivotal quantity? It's just a quantity for which the distribution here is independent of the parameters of my problem. Here I have two parameters because I deal with mu and sigma squared, the two parameters of the Gaussian. And here I have built a quantity that is totally independent. So a quantity that is based on the observation and the parameters, okay, and the number of observation, that is independent of the, okay, independent of the parameter in distribution. So why it may be interesting for us to have this? Because I can say the following. The probability that 1 over n sigma sum from I equal to 1 to n xi minus mu greater than minus a, I can compute it as the probability that n01 is between minus a and a. So it means that I can find, and I will see how just after, find a such that, for example, this probability is equal to 95%, for example, or 99%, or maybe more. Okay, but in general, okay, it's the level that we are going to consider in this course. Okay, 95%, excuse me. So to do this, so at this time, okay, I want to solve the following. That is to find a such that the probability that my n01 is less than a and greater than minus a is equal to 0.95. Okay? What is this? In fact, I can express this quantity using the distribution function of n01. I can write it as the probability that my n01 is less than a minus the probability that my n01 is less than minus a here. Keep in mind that here I am in the case of continuous random variable, so I can put large or strict inequality everywhere here, and it changes nothing, okay? Because for a continuous random variable, the probability to be equal to a point, okay, is always equal to 0. Okay. Keep in mind that here you have, let's say, the Gaussian density function. So sorry for the picture, but something like this. It is symmetric with respect to this axis, okay? And I can see that the probability that my n01 is less than small a here, that is this probability, this area here, that is the integral of the density function from minus infinity to minus a, is equal, in fact, to the probability that I am greater than a. And both areas are equal because I have the symmetry of the density function with respect to this axis here. So I have this one that is less than a minus, okay, the probability that my n01 is greater than a, small a here. And I can express this one using the distribution function in the sense that I have here the probability that my n01 is less than a minus 1 minus the probability that my n01 is less than a using the probability of the complementary set, okay? And so I obtain at the end 2 times the probability that my n01 is less than a minus 1. So I want to solve this one equal to this one. And in other words, I want to solve, okay, P of my n01 less than a is equal to 1.95 over 2, that is 0.975. Okay, so it's what I want to solve. And now to obtain this, in fact, in order to obtain this, so you know that I don't have an explicit form for the distribution function of n01. I don't have an explicit form, but I have tables, okay? I have tables. And you have here, for example, here, one table where here you have the distribution function of n01, okay, for a certain point z. And keep in mind that I want to find, okay, such a point here for which what I obtain is 0.975, okay? And I see though in this table, okay, what I see is that I have here the value I want, 0.975, and this is obtained for z equal to what? So I see that I have this line here and this column. So it will be for z equal to 1.9 plus 0.06. So for a equal to 1.96. That is exactly written here because it's a very particular and famous value for the Gaussian, the standard Gaussian distribution function. So if I come back to what I want to do, okay, the a I found here is a equal to 1.96, okay? And if I come back to my initial problem, what is my initial problem? Okay, keep in mind that I was building this probability here. and find an A such that this probability is equal to 95%. Okay, so let's continue with what I have done. Okay, I have proved that the probability that 1 over n sigma sum from I equals, so it's the square root of n, excuse me, sigma sum from I equal to 1 to n of xi minus mu and less than 1.96, this one is equal to 95, in fact 95%. Okay, I have this one. Okay, so I can express this one in a slight different way. Okay, if I want to make appear the sample mean here, instead of here I have the sum of the xi, I can make appear the sample mean, and I see that this quantity is none other than square root of n over sigma xn over line minus mu. Okay, so do the computation and you see that you will obtain exactly this quantity for this one, and having in mind that my xn over line is just the sample mean. Okay. And so using this, I find a confidence interval for mu. That is the probability that mu, that is my quantity of interest, belongs to, so to what? Okay, so what I have to do, I have to multiply by sigma, and I have to divide by square root of n, and then, okay, I have to subtract xn over line. So I obtain something like this, okay, in the construction of the confidence interval. The probability that mu belongs to xn over line minus 1.96 sigma over the square root of n, xn over line plus 1. So be careful because here, okay, I have to distinguish between both. You have a 6 here, and here you have a sigma, okay? So 1.96 sigma over the square root of n, and this probability is equal to 95%. So you have here, for Gaussian distribution, the confidence interval for mu of level 95%. Okay. So what is the size of the confidence interval here? So the size of the confidence interval is 3.92, okay, sigma over n. Okay, so if I want a certain level of precision for my approximation of mu by xn over line, okay, but I just have to fix a level of precision for this quantity, that is the size of my confidence interval. And typically, okay, so a numerical example, if I take sigma equal to 1, okay, and if I want a size for the confidence interval with the square root here, that is equal to, let's say, 0.01, I obtain a n that is equal to this one, 143,664. So for a confidence interval of size 0.01, if my sigma is taken to be 1, okay, I obtain for n this quantity to be sure to have, okay, a confidence interval of probability 95% and with a size that is 0.01, okay? But remind what we have done previously, because, okay, in the preceding video, we have seen how to build confidence interval for the mean of a particular distribution without any hypothesis concerning the distribution, except the fact that I have random variables in L2. And we have seen together that from the Chebyshev inequality, it is possible to build confidence interval. And if you remind, so I have to recover what we have done previously. I don't know where is it, but we are going to find, okay? So maybe it was here. Okay, so it was the idea to compute the confidence interval using here, typically the Chebyshev inequality, okay? Because, okay, I know the mean square error relative to the sample mean that approximates the mean, okay? And then I have done a little numerical example in this situation where, in order to obtain a confidence interval of this level, if I fix my size of the confidence interval to be, as previously, that is 0.01, I need to take a n equal to 800,000. So, of course, this number is huge with respect to the one I have obtained that is around, okay, 150,000, okay? But it's because in this situation, I use an approximation. The inequality that you use here, that is the Chebyshev inequality, allow me to have, okay, a bound, let's say, for my confidence interval that is not optimal. But if I am in the Gaussian case, since I am able to find explicitly what is the distribution of the sample mean, I am able to build interval that will be more and more precise for the same, okay, computational effort, in fact, okay? So it's exactly what I can deduce, that when I have my Gaussian hypothesis, okay, I can use a more precise result. I can use a more precise result, okay, in order to build a confidence interval that is once again also built on the sample mean, the same, okay? But here, the number of observations that you need to have in order to obtain, okay, this level of precision that is the size of the confidence interval that is 0.01 is smaller and smaller with respect to what I can obtain for from the Chebyshev in the first part of the sampling session, okay? So for the mean, okay, I am in this situation. But there is a but here. There is a big but. Because if I want to do this explicitly, have in mind that here I have fixed my sigma equal to 1, but I have to know sigma. If I don't know sigma, okay, I will have a theoretical confidence interval, but if I don't know sigma, it won't be possible to obtain what I want, okay? And typically, okay, this result is a nice one that it's not possible to use in practice if you don't know sigma. And we are going to see, okay, in a few minutes, how it will be possible to do the job, okay, for Gaussian distribution. So I have a nice way to compute confidence interval here from the sample mean that is more and more precise than what you can obtain, okay, in the Gaussian situation from the Chebyshev inequality, let's say. But from a practical point of view, if I want to approximate mu, it means that in general, I don't know the related variance, okay? And so you have here a theoretical confidence interval that is useless in practice because you need to know sigma in order to find it explicitly, okay? So you will see in a few minutes how to overcome this problem. And to overcome this problem, we will have something that is in relation, in fact, with the student distribution. So let's continue this one. Okay, so in this slide, so I will go quickly because you know this, we have already done it together. I remind the definition of the chi-square distribution of parameter k. I have defined it as a gamma distribution with parameter k over 2, 1 over 2. So you have this density function, okay? We have computed together the expectation and the variance of a gamma. So you have the expectation and the variance of a chi-square of parameter k. We have computed together the moment generating function of a gamma. So you have the moment generating function of the chi-square. And be careful that this moment generating function is not defined everywhere, but we have a condition on t in order to be able to define it here. T is strictly less than 1/2. And we have also seen, okay, it was the aim of the exercise 5 of the list 6 of exercises that I can build a chi-square distribution of parameter k. Okay, it's a result that you can prove by induction, for example, very easily using moment generating function. I can obtain a chi-square of parameter k from the sum of the square of k independent n0, 1. It's an equivalent way to define a chi-square of parameter k. You can define it by its moment generating function, you can define it by its density function, or you can define it as the sum of the square of k independent n0, 1. Okay? And of course, from this result, from this theorem A3 that we have already proved together, okay, I can apply it to the case of Gaussian random variable that are not centered because it's sufficient to make it centered, okay? So you have exactly the last line, okay, that tell you that if you have independent n mu sigma square, if you do the sum of this square here, you obtain a chi-square. And why? But because simply here, if you take xi, if you subtract the mean and divide by the standard deviation, you have here an affine transform of the initial xi that is just a n0, 1. So you come back to this case, and so it's possible for you to use the theorem A3. Okay, so I have this one. And the chi-square here will be used in order to prove the following. So in fact, we are going to find a pivotal quantity here. And keep in mind that I have defined the pivotal quantity as something, okay, that have a distribution independent of my parameter of interest, okay? And we are going to find something. So in the previous part here, I have found something concerning the sample mean, okay? The sample mean, a pivotal quantity for the sample mean. And now we are going to do the job for the corrected sample variance, okay? And we are going to see how to do this. So first, let's prove the following result. That the sum from I equal to 1 to n of xi minus xn over line square follows a chi-square distribution of parameter n minus 1 if my xi are iid n0. So you have the sum here of n different squares, but be careful because inside here you don't have random variables that are independent, okay, because you have xi minus xn over line, okay, inside. So it's a real theorem that I have to do. It's not just from the definition of the chi-square, because here you have n term in the sum, but you have a chi-square of parameter n minus 1, not of parameter n, okay? So let's do the job of this one, okay? So the way we are going to do is the following. So proof of theorem A4. And of course, the way we are going to prove, okay, if you see the following, you have a complicated density function for the chi-square. Okay, so we are mainly going to use, okay, what we know about the moment generating function of the chi-square distribution. Okay. So I start from the sum from I equal to 1 to n of xi square. I know what is the distribution of this one. This one follows the chi-square of parameter n by definition, because you have the sum of the square of n independent and 0, 1 here. So you have a chi-square of parameter n. And we are going to introduce xn overline in this expression in order to make appear a quantity of interest here. I do the job this way. I just add and subtract xn overline here, okay? So let's do the computation. So what I will obtain if I do the job here, I obtain the sum from I equal to 1 to n of xi minus xn overline square. That is my quantity of interest, what I want to study here. That is this one, okay? Plus, so I have the sum of the xn overline square. So just a minute, okay, because I have my little daughter that is here. So what do you want, si tu veux? There you go. So you see my little daughter somewhere, okay? So sorry for this, okay? She needs her glasses, in fact. So then I have the square of this term, but I have, okay, n element in my sums here. So it is n times xn overline square, okay? I have this one, and plus what? So I have the double product here, that is 2 times, okay, what? So xn overline sum I equal to 1 to n of xi minus xn overline. Okay, but keep in mind that xn overline here, xn overline, okay, so or n times xn overline is just equal to the sum of the xi. Okay, so here, when you do the sum of the xi minus, in fact, n times xn overline, you obtain here something that is simply equal to 0. Okay, so if I continue my computation here, I obtain that the sum of the xi square from I equal to 1 to n is equal to the sum of 2 terms, the sum from I equal to 1 to n of xi minus xn overline square plus n times xn overline square. Okay, so what I know and what I want. So what I want is to have the knowledge of this one. Okay, what I know is that this one follows the chi-square of parameter 1. What I know about the distribution of this one, keep in mind that this one may be written as what? As the square root of n xn overline square. But we have seen together that the square root of n xn overline follows n01, okay, in the case of independent n01. And so you have here the square of n01. So you have typically for this one, the chi-square of parameter 1. Okay, so you have here a chi-square of parameter n, and you have here a chi-square of parameter 1. And what can I say about these quantities here is that both quantities here and here are independent. Why they are independent? So let's come back to a previous slides, okay? Maybe this one. The fact that xn overline is independent of the sum of the xi minus xn overline square. So by theorem 2 here, excuse me, by theorem A2. Okay. So now if I want to compute the distribution of this one, I can use, okay, let's say moment generating function. And I can say that the moment generating function of the sum from I equal to 1 to n of the xi square at the point t will be equal to the sum from I equal to 1 to n, excuse me, will be equal to the moment generating function of the sum I am interested in. At the point t, multiply by independence. Since I have the independence, I know from my course concerning moment generating function that the moment generating function of the sum will be the product of the moment generating function here. So I know what is this moment generating function because it is the moment generating function of a chi-square of parameter n. So moment generating function of a chi-square of parameter, okay, so here it's the chi-square of parameter k, but I have here in my previous slide the chi-square of parameter n. So that is well defined for t strictly less than 1/2, okay, and I obtain 1 over 1 minus 2t to the power k over 2. So I have here, so my t has to be taken strictly less than 1/2 here. It's exactly, I repeat, what I have in this slide here. My t has to be strictly less than 1/2. And I obtain for this one here 1 over 1 minus 2t to the power n minus 1. This one is a chi-square of parameter 1. So I have 1 over 1 minus t. Excuse me, it's not n minus 1 here. Okay, so have a look. It's not n minus 1, it is n over 2. Okay, so I have here n over 2. Here I have to the power 1/2, from which I deduce that this one is equal to what? But this one is equal to the ratio of this one and this one. So this one is necessarily equal to 1, okay, over 1 minus 2t to the power, okay, n minus 1 over 2. And I obtain for this quantity the moment generating function. And I see that this moment generating function is none other than the moment generating function of a chi-square of parameter n minus 1. So I have proved my results. I have proved that this sum follows a chi-square distribution of parameter n minus 1. Okay? So this result theorem A4 is true for xi that are n0. So in the corollary A1, okay, I start not with n01, I start with n mu sigma square. So my x1, xn here in the corollary A1, so I am here. IID n mu sigma square, okay? I have this. Of course, I can use the following transform in order to make them centered and reduced, okay? So that is to obtain standard Gaussian random variable, okay? So the xi here, I obtain IID n01, and so I can use my result. That is the sum from I equal to 1 n of yy minus yn over line square follows a chi-square of parameter n minus 1, okay? Why not? And I can see that this one, if I replace yi, okay, by this quantity here I obtain simply, okay, so do the computation at home if it's not clear for you, okay, but it's obvious, 1 over sigma square that comes from this one, and then I have a simplification between the mu here. So sum from I equal to 1 to n of xi minus xn over line. So this quantity follows the chi-square of parameter n minus 1. Okay, but what is interesting with this quantity is it's in fact that it is related to the corrected sample variance. Keep in mind that I have defined Sn square. I have defined it as n over n minus 1 times the sample variance, this one. And so this quantity is just equal to 1 over n minus 1. So let's do n. 1 over n. The sum from I equal to 1 to n of xi minus xn over line. Okay? Square. I have simplification between this term here, and I see that the corrected sample variance is just equal to this sum divided by n minus 1. Okay, this sum divided by n minus 1. And so I see that if I multiply the corrected sample variance by n minus 1, and if I divide it by sigma square, what I obtain for the corrected sample variance, here I obtain 1 over sigma square. Okay, so the n minus 1 simplify here, and I obtain the sum from I equal to 1 to n of the xi minus xn over line square. And I know from my previous result here that this one follows the chi-square of parameter n minus 1. I have a chi-square of parameter n minus 1. Okay, so I have this one. And this quantity is what we call a pivotal quantity, because once again, I have a distribution here that is independent of the parameters of my problem here that are mu and sigma square. I have no more mu and sigma square here. And in fact, this one, with this one, we are going to be able to build confidence interval for, okay, the variance of n mu sigma square. So let's do the job. I know that n minus 1 Sn square over sigma square follows the chi-square of parameter n minus 1. Okay? So I can say the following, that the probability that n minus 1 Sn square over sigma square greater than a and less than b is in fact the probability that the chi-square of parameter n minus 1 is greater than a and less than b. So here be careful, because in the case of the Gaussian random variable, I have taken, okay, a confidence interval that was centered around the sample mean. But here keep in mind that my chi-square, okay, if I plot the density of a chi-square, I obtain something like this. It's a density over R plus here, okay? The density of a chi-square here of parameter, let's say n minus 1. Okay, so I can't take, okay, intervals that are centered around 0. It's meaningless to do this because I have simply positive value for my chi-square, okay? And from this one, I can deduce that this is equal to the probability that sigma square belongs to what? Okay, so belongs to n minus 1 Sn square over A. And here I have n minus 1 Sn square, okay, over B. And the idea is to see, okay, so here you have a confidence interval. And this confidence interval is related to this quantity. So here, if I have here A and B, my probability of interest here is this area here. The area is this probability here, exactly. And my idea, okay, is to find A and B in order to obtain, okay, in order to obtain what? But in order to obtain, let's say 95%, for example, okay? So here, what is the idea to find A and B such that the area in red here, that is this probability, is equal to 95%. So this one. Okay, but in fact, we can obtain it because we have tables for the distribution function of chi-square random variable. Okay, we have this. But here, okay, it's slightly different than what you obtain for the Gaussian, because I repeat, for the Gaussian, we have things that are centered around, okay, 0. So I have symmetric intervals here. It's not the case here, of course. But if I see this quantity of interest here, the probability that my chi-square of parameter n minus 1 greater than A less than B, okay, I can express it using, okay, distribution function. It is the probability that my chi-square of parameter n minus 1, okay, is less than B, plus, or in fact minus here, the probability that my chi-square of parameter n minus 1 is less than A. Okay, so I have this one here, the probability that I am less than B minus the probability that I am greater than A. Okay, we are going to write it, okay, we are going to write it this way. It's the probability that my chi-square of parameter n minus 2 is less than B. So we are going to express this probability using the complementary set, okay? That is, okay, to obtain, or in other words, so to be clearer, okay? To be clearer, I want to obtain, well, let's write it, okay? So minus 1 minus the probability that my chi-square of parameter n minus 1 is greater than a. I can put a strict or a large, whatever, because I deal with continuous density. Okay, so in other words, I want things such that, okay, if I want to obtain a level of 95% here, I have to find a b, a, such that the probability that the chi-square of parameter n minus 1 is less than b, plus the probability that my chi-square of parameter n minus 1 is greater than a, is equal to what? 1.0.95. Okay. Yes, I have this. Okay, 1 plus this one. Okay. And the idea is to take, in order to obtain this one, so if I call this one, okay, let's say alpha, okay, I find a b such that this one will be equal to 1 plus alpha over 2. In general, it's the way we do. And this one is equal also to 1 plus alpha over 2 in order to obtain this one. Okay, so find b such that I have this, and find a such that I have this. And if I give you the number of observation, you will have a chi-square with a parameter, and you will be able to obtain from tables the capital B and the capital A that fulfills this equality here in such a way that you will obtain a probability here equal to 95% that will allow you to build this confidence interval that will have, okay, a level of 95%. So find A and B may be obtained as I have explained here, okay? And then I obtain this way a confidence interval for sigma square. And here it's a real confidence interval in the sense that from observations, I am able to compute it explicitly. Okay, in the case of the sample mean, okay, and mu, I have built previously a confidence interval using the Gaussian sample mean, but this confidence interval was dependent of the variance or the standard deviation. So it was useless in practice, but here, for the variance of Gaussian, I have a real way in order to build confidence interval. Okay? So I continue, because now we are going to see, okay, in relation with what I have just said before, for the mean, for the moment, I don't know to use how to obtain in practice confidence interval. I have a theoretical answer, but that don't allow me to build confidence interval because it depends on the standard deviation I don't know. I want to overcome this problem, okay? To overcome this problem, we are going to do a little reminder concerning, okay, the student T distribution. Okay, so I won't spend too much time on this student T distribution because you have studied it, okay, in your homework, okay? So let me just remind you that I can define the student density function this way, where gamma is the gamma function here. It has an expectation equal to 0 for k strictly greater than 1, and a variance that may be expressed this way for k strictly greater than 2. And in fact, as in the homework, the way we can obtain this density function is to consider a student as a ratio of what? The ratio of n01 and of the square root of u over k, where u follows the chi-square of parameter k. And I suppose that z and u are, okay, independent. So I obtain a student of parameter k through this transform, where z is n01, u okay, is a chi-square of parameter k, and they are independent. Okay, it was exactly the aim of one of the exercises of you or more to prove that this random variable defined this way as this density function. And from this result, okay, we have the following nice result. That is here, okay, this quantity here follows a student of parameter n minus 1. So let me remind what we have seen together already. We have seen together that if I start from my independent n mu sigma square here, we have seen together that the square root of n, xn over line minus mu over sigma follows n 0, 1. And I have built this way a confidence interval, I repeat, but a confidence interval depending on sigma, a quantity that I don't know a priori. What is the meaning of the theorem? It tells me that, in fact, in this expression, I can replace sigma by we have seen together that Sn square was an estimator for sigma square, okay, that was unbiased, okay, and if I take the square root of Sn square, it will be an estimator of sigma. And if in this expression I replace sigma by the approximation I obtain from the corrected sample variance, this resulted me that the square root of n xn over line minus mu over the square root of Sn square follows a student of parameter n minus 1. Okay, so I pass from the Gaussian to the student if I replace the theoretical variance or the theoretical standard deviation by the corrected, okay, the square root of the corrected sample variance. But here I have something that is independent of sigma. So I will be able, I won't do it because it's always the same thing. I will remind briefly what are the things for this one, okay, but I will be able to build this way a confidence interval for mu from this quantity and from the tables of the student t distribution of parameter n minus 1, okay, and a confidence interval that I will be able to use in practice because here, okay, you have a quantity that is independent on sigma. So I will have a confidence interval that will only depend on my observations, okay, and the number of observations. So to prove this result, it's very easy. In fact, the only thing you have to remind is the definition of a student. So a student of parameter k is a n01 divided by a square root of a chi-square of parameter k over k. So my student t of parameter n minus 1 can be written in distribution as the n01 divided by the square root, okay, of what? Of a chi-square of parameter n minus 1 over n minus 1, and with the fact, of course, that my n01 and my chi-square have to be independent. So it's the way to define from the previous slide, okay, a student distribution here. Okay, so I have this one. So let's see what I know from what I have done previously. Previously, we have seen together that we have this. N minus 1 Sn square over sigma square follows the chi-square of parameter n minus 1. So n minus 1 Sn square over sigma square follows the chi-square of parameter n minus 1. So let's write it. So n minus 1 Sn square over sigma square follows the chi-square of parameter n minus 1. Okay, and where I remind you that Sn square is just equal to 1 over n minus 1, the sum from I equal to 1 to n of xi minus xn over line square. Okay, we have also seen together that square root of n xn over line minus mu over sigma follows n01. It's what we have seen previously. And we also have seen together that this quantity and this one, okay, so that xn over line is independent, in fact, of this one. Okay, so this one and this one are independent, implying that this one and this one are, of course, independent from what we have seen previously, independent. Okay, so if I use this, how to define a student T, but I start from my N01. Okay. I divide by the square root of what? Of my chi-square. My chi-square that I have to divide by n minus 1. And I obtain this way a T of parameter n minus 1, and by definition. And if I simplify a little this expression here, I see that I have simplification between the n minus 1 here and the n minus 1. And I will have a simplification between the sigma that is here and the sigma that is here, because I have the square root of sigma square with sigma that is chosen to be positive here. So at the end, I have what here? I have simply the square root of n xn over line minus mu over the square root of Sn square. And that is exactly the quantity of interest in the theorem here. Okay, so doing this little manipulation here, I prove that this random variable may be written in fact as the ratio of n01 and then the square root of a chi-square of parameter n minus 1 over n minus 1. That is exactly the definition of a student of parameter n minus 1. Okay. And quickly, because I have already done several times here, I can build a confidence interval of level 95% here in the case of the mean of a Gaussian, thanks to the student distribution, because I know that I have this quantity here that follows the student. So this quantity that is, where is it? So here, excuse me, I erase this one. No, excuse me. I erase this page here that I don't need. Okay. So I have what? Square root of n xn over line minus mu over the square root of Sn square. If I wanted to take this probability, it is the probability that a student T of parameter n-1 greater than A greater than B. And I will have tables to compute this kind of quantity and make it so if I choose A and B in a good way, I will obtain 95% for this one here. And this one may be written as what? Okay, so I can write it this way. I will do it in several steps. Okay, so I can multiply by the square root. Okay, so I will have the square root of Sn square here time A divided by the square root of n minus xn over line that is less than minus mu and greater than what? Okay, b square root of Sn square over the square root of n minus xn over line. And I obtain this way the probability that mu belongs to a random interval of the form, okay, just I have what I have done here, I have done it this way, just be sure that I don't do mistakes. Okay, yes, I have this. So I have mu that is greater than xn over line minus b square root of Sn square over the square root of n. And here, xn over line minus a square root of Sn square over the square root of n. And you have here, okay, a confidence interval from mu. That is a real confidence interval, not in the case, okay, where I have something that depends on the standard deviation of the distribution. Here, I only depends on the observations, okay, the xi and the number of observations small n, and A and B can be obtained, okay, but from the distribution function of the student T of parameter n minus 1. Okay, so I have an answer for the mean this way, and for the variance through the chi-square distribution, where I am able, okay, to build confidence interval in the case of Gaussian samples. Okay, and I will just finish this session by small remark, okay, because in your homework, okay, I have defined the F distribution. In your homework, I have defined the F distribution, okay? So I have defined the F distribution of parameter M and N as what? As the ratio of U over M and V over N, where U and V are two independent random variables, where U follows the chi-square of parameter M, and V follows the chi-square of parameter N, okay? And we have proved, you have proved during the homework that this kind of random variable, that is a positive random variable, has this density function, and that we are able to deduce, okay, its expectation and its variance, okay? But for me here, my F distribution will be the ratio of two chi-square, okay? So let's use this result in the following way. So here, so just a little misprint in my slide here. Here it's not yn, here it's just yn plus 1, okay? So I have here, and in fact I will modify a little this one. We are going to modify it, in fact, a little. here in my statement, I will take here for x a sigma 1 here and a sigma 2. I allow them to be different. Okay, so in fact, you have a m plus 1 sample of n mu x sigma 1 square. You have a n sample of n mu y sigma 2 square with variants that are different here. And I suppose that both samples are independent. So I have m plus 1 observation of a distribution, n plus 1 here observation of another distribution. And I suppose that these two sets of observations are independent. Okay. And I said that, so I have to modify slightly my, my slide here. I said that in this situation here, if I multiply by 1 over sigma 1 and here multiply by 1 over sigma 2, this ratio follows an F distribution of parameter M and N. So first we are going to see why, okay, and then we are going to see what may be the interest of such a situation. Okay, so you have a set of observation, okay, of a particular Gaussian, another set of observation for another Gaussian. I suppose these observations that are independent. I suppose that they are independent, and I have this ratio that follows an F distribution. Okay, so the result, the underlying result that we are going to use is the one we have proved previously. That was this one, n minus 1 Sn square over sigma square. Okay, follows the chi-square of parameter n minus 1. And in fact, if I do this, okay, I have to modify what I have said here. Here it will be sigma 1 square, and it will be sigma 2 square here. So let's check. It's not complicated to have this. I know, okay, that, so what I know. If I have x1, xn that are IID n mu sigma square, I know that n minus 1 Sn square over sigma square that will follow the chi-square of parameter n minus 1. Keeping in mind that this one here, this quantity, is just the sum from I equal to 1 to n of xi minus xn over line square over sigma square. But what I have here, but it's exactly what I have. Because if I write what I have written here, what I have the sum I equal to 1 to m plus 1 of the xi minus x m plus 1 over line square over sigma 1 square m. And then I have another expression that is the sum from j equal to 1 to n plus 1 of yj minus y n plus 1 over line square over sigma 2 square n. Okay? What I know from this result? I know from this result that here you have a chi-square of parameter m. From this result, you have also here a chi-square of parameter n. Okay? And I know from my statements that these two sets of observation are independent. Here I have something that depends only on the xi. Here I have something that only depends on the yj. And so that these two random variables are independent from my statement here. So what I have finally here, I have a chi-square of parameter m divided by m, divided by a chi-square of parameter n divided by n, and the two chi-square are independent. If I come back to the definition of the F distribution, I will have exactly what I want. That is my quantity of interest here, that is this one here, follows an F distribution of parameter m and n. Okay, I have this. And to conclude, okay, so I won't use this one. Okay, erase. I will just reproduce this. In order to conclude concerning this, what I can do with this kind of results, but once again, we are going to build confidence interval this way, based on the F distribution. And which quantity is the quantity of interest here? But the quantity of interest will be the ratio of the variances. Sigma 2 square over sigma 1 square. Okay, so we'll be able to build confidence interval for this quantity, because I have this quantity that deal with this one here, because I have 1 over sigma 1 square over 1 over sigma 2 square here, multiplied by something, okay, that is just something that depends on the observations, follows an F distribution, and you have tables for the F distribution, okay? And so in this situation, you will be able to find confidence interval for this, and typically you will be able to find confidence interval to see if, for example, from these two sets of observation, you can deduce that the two variants are equal or not. Okay, it's one way you can do. And typically, okay, when we are going to do tests, okay, in the 2 sessions, we will see, maybe if I have the time to do that, this statistic here, this estimator, allow me to build a test, okay, to check if the variants are equal or not, okay, in these 2 random samples, 2 independent random samples of Gaussian distribution. Okay, so it concludes the session concerning sampling. And in the next session, what we are going to do, here you have seen that we have obtained estimator for the sample mean, for the mean, and that is the sample mean, and for the variance, that is, let's say, the good one, that is the corrected sample variance. We have used them in a Gaussian setting in order to be able to build confidence interval, okay? And what we are going to see in the next session is to say, if we can deduce that the sample mean and the corrected sample variance are the best possible estimator, because for the moment I have estimators, okay, but there are possibilities among, okay, a big set of possibilities, in fact, and I want to be able to deduce, okay, if they are the best among the possible set of estimator for the quantity of interest. And we will be able to do this, okay, using the part concerning estimation, where we are going to prove that in particular situation, okay, there is a bound that exists that is called the Kramer-Rao lower bound. That is a lower bound for the mean square error of an MDS estimator that will allow us to check if our estimator of interest is the best or not among all of them. Okay, so see you next session for estimation.